It's called the Copernican Revolution. Okay, you can read this caption. Was Copernicus right?
Yes.
Yes. Yep. Copernicus was back to the sun-centered model. I kind of call the Ptolemy like he was the last gasp of the Earth being in the center and everything orbiting around the Earth. Like, nice try. So this is the Copernicus model. In the middle it says Sol, right? That's the sun. And these little circles, although we're gonna deviate a little bit from this, these little circles are the orbits that the planets make around the sun. Okay, I'm going to add a name, Brahe. I'm not sure I'm pronouncing that right. But if I were to show you the video, and I'll skip to this video for now, but Brahe actually was before telescopes. Okay, Brahe was another scientist. And this fancy contraption, basically he looked at the angle of where objects were. So he could see the stars moving. Okay, Brahe. What did we find out on last Wednesday about planets? Do planets, when you see Jupiter in the sky, is Jupiter always going to be that same location with those other stars? No, the word planet means wanderer. Jupiter's going to wander. It's going to wander one direction, and then it's actually going to wander the other direction a little bit. The other thing about Tycho, and we'll talk about this later, is that he observed a star blowing up. Does this look like a star blowing up?
Looks like a pimple.
Looks like a what? It looks like a pimple. This is actually not the star blowing up, but this is what we call the remnant from the star blowing up. It's called a supernova remnant. When the star blows up, we call that a supernova. There are various conditions to make two types of supernova. One of the important things about Tycho Brahe seeing a supernova was that, how do I say this? Can you imagine and for 2 weeks it was really bright. Can you imagine Tycho making his measurements and then all of a sudden he sees something bright in the sky? Like, here's a constellation, it could be the Big Dipper, and all of a sudden you see another star. Oh crap, where did that come from? It's come from a star blowing up. Now it only stayed really bright for a couple of weeks. But one of the things is that actually that bucked the, how do I say this? I'm going to put it this way. Religion is not equal to science. Now, like I said, I'll be glad to talk to you about my own faith outside of class and all that, but religion is not science. I mention this because when he saw that bright star appear, everyone's like, dude, the heavens are perfect. That was a religious tenet. Heavens are perfect, and that just doesn't happen. So kind of keep that perfection thing in mind. We'll say, so he also observed comets. And again, we're going to talk more about comets, but, well, right off the bat, comets, and if this is my sky, one of the things about comets is they aren't like a jet. You know how a jet goes across the sky and leaves kind of that tail? Okay, comets actually will move this much over the course of an entire evening. And then so a comet will be here, then the next evening a comet will be here, the next evening it'll be here. So eventually a comet will move across the sky. And what's happening with a comet is what's happening with the planets is they are orbiting the sun and we are seeing them move. So the comets will move like that. So he saw comets.
So a shooting star is a comet, right?
A shooting star is a meteor, kind of, in comets, and they're similar origin.
Do meteors move as slowly as comets?
Like meteors streak.
Okay, I was
Meteors
going to say,
streak.
because like on TV shows and movies, it always goes super fast. So
it does. Yeah. And a really crazy meteor was the one in Russia that was caught in Russia. They have like terrible driving conditions, so everybody has like a little thing on their car to catch
the dash cam.
Dash cam, yeah. So yeah, there's a really famous one, and meteors go fast. The thing about a meteor is it's a little piece of a debris that's falling through the Earth's atmosphere. The thing about a comet is it's still out there. It's way out there probably, and it's just orbiting the sun. And it's flaring a little bit because it's getting close enough to the sun that's kind of melting and making that kind of tail that some comets have, some comets don't.
So meteor shower is just a bunch of them?
Yep. Meteor shower it's where the Earth, okay, so the Earth orbits the sun, where the Earth plows through kind of, like, think of, and there's like a little image coming up like this. So think of this. The Earth is going to plow through those little tiny things. And that little pile of bits was probably left by a comet that orbited the sun and kind of fell apart there. So every time as we orbit the Earth, okay, we're going to get that meteor shower. And then we come back around here, we get that meteor shower. So it happens at a certain time each year. Yeah. Good questions. The next one I'm going to put up is Kepler. So one of the things about science, and I said this to my my chemistry students the other day, is that it just keeps building on itself. We don't start all over when a new generation of scientists are born. The next name actually is going to be Kepler. So the way I think the story is told is this, that Brahe actually hired Kepler. Brahe made lots of observations. Remember, he had that fancy, he was nobility. He had that fancy angle thing. And he's like, I cannot make sense of the data that I have collected. So he gave it to an astronomer mathematician, Kepler. So Kepler actually made some breakthroughs with regard to the whole, how does the solar system work? Okay, and of course, it wasn't this way, like Ptolemy said. It was this way. But there are 3 laws that he came up with. One of his laws, can you see, what would you say about that sun or the star? What I drew on the board? Is it in the middle?
It's closer to one side of the orbit than the other.
It is closer. And I did that on purpose. That's one of Kepler's laws. Kepler's laws are all about how the planets orbit the sun. Okay? So, one of the things, and I don't know if I did it here, but what's an ellipse? Do you guys know? Do you know what an oval is? Yeah, exactly. It's kind of an elongated circle. That's what an ellipse is. And so he said that this shape is elliptical, and that's kind of circular, but makes it look a little elongated there. And he said that the sun is off-centered, okay? And I'll kind of talk you through his 3 laws. So here's his 3 laws, okay? First off, we need to ask what an ellipse is, and on this figure, you can kind of see circle, ellipse, parabola, hyperbola, okay? And this isn't a math class, but you can get all those shapes by conic sections from a cone. Yeah, but no math. But focus on ellipse. All right, does that look like an oval or an ellipse, hopefully?
Yeah.
Okay, good. So the blue line there is the orbit of a planet as it goes around the sun. So this is an ellipse, and actually how circular or how kind of flattened out it is called the eccentricity of that circle or ellipse. It has an eccentricity of, I believe, 0 if it's totally circular, and it gets elongated, the eccentricity increases. So now, we've got a few things here. This word, you pronounce it perihelion. I kind of think as peri, you're kind of close to something. Helion meaning sun. So perihelion is the place, in all the planets have it, it's the place in our orbit where we're closest to the sun. Now you might say, I bet that's June or July. Nope, it's actually January. Perihelion, yep. So this is around, what did I say, January? And this is around July.
Do we still follow these laws?
Yes, the planets, as they go about the sun, still follow these laws. And it's kind of one of those deals where they didn't necessarily even know the thing of gravity yet. Actually, gravity is what tethers our planets, keeps them orbiting the sun, the force of gravity. We'll talk more about that. But this is his first law, so it gives the shape. And it says that with ellipses they have kind of, an important place called a foci. If your ellipse is circular, it only has one foci. If your ellipse is elongated, it has two foci. I call them belly buttons. So the sun, and it's like a mathematical thing, the sun is at one foci. Okay, and it's off-centered. We have perihelion, we have aphelion. That's it. That's his first law. Second law. Well, that's how you draw an ellipse. Okay, this is his second law. So I kind of do this with kind of, this is how I do it. See if it works for you. This is the sun. Okay. So if I am at perihelion, I better go counterclockwise. See, that's okay. So I'm going like this. Okay. If I am at perihelion, and I'm a planet, and it could be any planet, you know, Earth, Mars, Venus, Jupiter, Saturn, I'm going to go faster. So that's kind of what's shown there. You see the B part? When I go from position 1 to position 2, okay, here it goes. It goes, and I slow down. Out here at aphelion, I'm dragging. Here we have the same time between the segment 3, 4, and then I speed up. Okay, that's how they do it. So if you want to, just basically, I'm out of breath. Oh my gosh, I'm sorry. If you want to do this, this is at what we say perihelion. Fastest. That's it. That's it. This is aphelion. I can't read my own writing, but hopefully you can. Slowest. Now the law goes like this, that it sweeps out equal areas. All it's saying is that if you're out here, you're going slow. This segment is small, but this is small, but it goes a lot of area back to the sun. So that's it. The last one, actually, do you guys remember we talked about, we picked on Mars, and we said that when the Mars appears to go backwards in the nighttime sky, which planet moves faster, Mars or Earth? You guys remember? Mars.
It's Earth.
Earth goes faster. Yep. Thank you for answering that. Yes, Earth goes faster, and that's the pattern. That's Kepler's third law. He basically said, and it's a gravity thing, he basically said that the closer the planet is to the sun, the faster it's going to move in its orbit. Like, oh yeah, it's going to, like Mercury, the closest planet, is going to go fastest because it's got a smaller ellipse, okay, or orbit than Jupiter. No, that's true too, but literally it will move more quickly in its orbit, and Jupiter's kind of dragging along, all going counterclockwise. Okay, so that's his third law. And I know it says that p squared is equal to a cubed, but all that's saying is p is the period that it takes to complete one orbit about the sun, and a actually has to do with the ellipse, that it's the semi-major axis. But that's its third law. And we can kind of see this here, where we have distance from the sun, increases distance from the sun, and look what's along the x-axis. This is actually then decreasing speed as you increase distance. That's what this graph is showing you. We have some graphs in this class, and that's what that's showing you. It's not a linear relationship, but it's got a square-cube relationship that somebody found out a long time ago. That's pretty impressive. Okay, so that's Kepler, Galileo. So actually, after Ptolemy is about the only Earth-centered person up here. Everybody else has got a heliocentric model. So Galileo, Does anybody know anything about his life? Right off the top of your head. What do you think of Galileo? Nothing comes to mind.
Bohemian Rhapsody.
Bohemian Rhapsody? Oh, Galileo. Okay. Well, that. But Galileo. There's been definitely books written about him. I think there's been a book written about his daughter, Galileo's daughter, because he was in they're all pivotal, but he was kind of breaking out of this sort of issue where religion is not equal to science. Staunch Catholic, but as the scientist in him said, I can be Catholic, but I can also observe and think and apply the scientific method. Okay? So, here's one. So, the first one up there, actually I brought a little prop on here. So, people are like, Ptolemy's got to be right. Remember Ptolemy's wrong. Okay? Because we can't orbit the sun, because if we orbited the sun, I'll show you what would happen. So if we orbited the sun, okay, we all see this. This is just water. What would happen to the water if I make the dish go fast? That way.
It would
fly out, exactly. So here we go. So what they said was, dude, if the Earth is orbiting the sun, one of the things we have associated with Earth is the Earth's air, the Earth's atmosphere. It's going to leave its atmosphere behind, right? That's what they said. And they're right. But actually, there's this thing called inertia, and we'll be talking about it as far as Newton's laws on Wednesday, that said if that, well, I can do this again. So I'm not going to go fast. I think I'm going to kind of accelerate slowly. But if I accelerate slowly, and then after I'm done accelerating, if I keep the same speed, that water is going to stay with that dish. Because the water has the same velocity as the dish. The problem here was I am accelerating versus going just a constant speed. Okay. So anyway, that's one of the things that Galileo actually kind of talked about. Item number 2, the problem with, again, kind of the religious saying that the heavens are perfect. The Earth is perfect. And to everybody, the Earth-centered model of the way things are, religiously speaking, they were more comfortable with it. The other thing, okay, this thing we talked about, parallax, they basically said if the Earth is here in January and then the Earth is here in July, said it's kind of like closing one eye, closing the other eye, those stars are going to be like scrambled. Okay, because of parallax. One of the things we know about parallax is the farther something is from your nose or whatever, the less parallax effects. Okay, and so that's actually what Galileo proved. So let's see how he did that. So he was able to address each one of these. Now, Galileo, you might have said, well, he was the first one, he invented a telescope. No, there were telescopes out there. I like to think of probably the first telescope was like the pirates. Okay, little telescopes, and he didn't do that. But instead of like looking for on the seas and stuff like that, he was early on to say, let's look at the heavens. Okay, the heavens with his telescope. All right, so the whole thing about the atmosphere. Okay, what Galileo saw was that if you have an object that's moving, that object will continue to move in that same direction with that same velocity unless something else acts upon it. So if we have the Earth here, and it's delicate, and it is pretty darn delicate, the Earth's atmosphere around the Earth moving like this, Well, the Earth will move and the atmosphere will move along with it. Okay? Newton's first law of motion. Here's one for you. He has a whole list of things that says that, that we are supreme and we are pretty cool, the Earth. There's all sorts of things out there that says, life happens. Nature is messy. And this is it. This is where we are in our system of planets. Okay, so one of them was Tycho's nova. Okay, Tycho Brahe's nova that he observed. Another one, and so what is this picture of? The moon. Yep. So starts with letter M. What do we call those dark areas?
Mari.
Mari. Awesome. What do we call the light areas? Starts with H.
Oh, no, that.
Oh. Think of mountains. Starts with letter H. Kind of like highlands. They're mountains, but we call them highlands. Highlands, yeah, the white parts of the highlands. So one of the things that he did with his telescope was he said, the moon, or maybe he didn't have to have a telescope. He's like, dude, life is messy. Reality is messy, and the moon's not perfect. Nor is the Earth, nor any one of us. Okay? So that was Tycho Brahe. Parallax. Okay. I said that parallax actually goes away. This is the whole thing. 6 months apart, we're different locations in space-time. So you're like, so the stars seem to be scrambled, make different constellations. He said not if they're too far apart. And one of the things, I'll bring my binoculars. If you bring binoculars tomorrow night, or even don't bring them tomorrow night, but use binoculars to look at the Milky Way. And he did that. And he used his telescope and looked at the Milky Way, and it's just gorgeous. All these stars. It just looks like a cloud until you use binoculars. Okay, so he's like, they're so far away that they look like fuzz to us. Okay, so parallax wouldn't work. Now I've got two models here: a model on the left and a model on the right. Let's see, which one's right, left or right? She says the right one's right. Do you think that's right?
Oh wait, no, I meant left.
So it says the left one's right. Is that right?
No, right.
No, she changed it to the right. How many people think the right one's right? How many people think the left one's right? Now look at these. Now we have the sun in the middle. Or we have the sun here. Here the sun is orbiting the Earth. And here the Earth is orbiting the sun. They are kind of confusing to look at. So how many people think the right one's right? Me too. Yep. We'll see tomorrow, 8:30. I'm not sure if it'll still be up, but if it is up, that might be one of the first things we look at is the planet Venus. Okay? So Venus is what we call an inner planet. Okay? Well, there's two ways to look at inner planets and outer planets. Venus is inner relative to Earth's orbit. What's the other inner planet? You know what? Mercury. Yep, we have Mercury, Venus are both inner planets. And as such, actually, from our perspective, they will go through phases. Like the moon, we talked about the moon's phase, quarter phase, a full phase, a new phase. So actually, one of the things I get excited about is seeing Venus go through these phases. Because we only see Venus because the sun hits Venus and we see that light. So if Venus is over here, we're only going to see a quarter. If Venus is here, kind of almost getting ready to come in front of us, or come between us and the sun, we're only going to see a crescent of Venus. Okay? So Galileo saw that, and he's like, well, dang, if that's the case, that actually supports the fact that Venus is on a track inside of us, orbiting the same object we are. We don't see that if Venus is out here, orbiting the Earth. Yep, the rest of the story. So he really came out. So he really came out solid with this one over here. Okay, and in doing so, it was not appreciated by his own faith, and so yeah, he was vindicated actually in 1992, way after his death. So I think that's interesting. Okay, so we're going to start on the next part so you do a few slides. But these are due. Somebody help me out. How many of these do you need to answer? 3 again? Okay. I didn't look, but whatever it said. Very good. Just 3 of those. Yay. Okay, so those will be due on Wednesday. So let's do a few slides with regard to Newton's laws. So yeah, Newton's laws, wait, first off, who can help me out? What's Kepler's first law? Do you remember? The shape of the orbits. Starts with an oval. If you put oval on the test, I'd be fine with that. But the shape is an oval, ellipse, yeah. Starts with an F. The sun is located at foci. Foci, yeah, focus. Center. Well, it's not, no, the sun's not in the center.
So the oval thing is called foci.
So the oval thing's called an ellipse.
Oh, so
And the belly button part,
is a foci.
foci, yep. His second law, remember I came over here, when does a planet move fastest?
When it's closest.
When it's closest, very good. And we circular P, we call that perihelion, yeah. We call this over here aphelion, yeah. What was Kepler's third law? And I said just use Mars and Earth as an example. What was Kepler's third law? Which planet moves faster?
Earth.
Earth. Earth moves fastest, yeah. So the closer a planet is to the sun, the fastest it goes. That's his third law. Now, Kepler's laws all only dealt with the planets. Newton's laws then deal with just objects. And how do I say this? Kepler's laws, which was way earlier, just the planets, actually jives, connects with, is consistent with Newton's laws of everyday motion. So I just think that's pretty darn cool. So we're going to talk a little bit about Newton. Again, it wasn't specific to astronomy. So, you know, we're kind of getting out of the whole planet thing, okay? Just everyday motion, every day. Could be the motion of this pen. Could be the motion of your car. Could be the motion of us walking across. We talk in terms of these everyday things, like speed. Speed, how fast do you move? Now, again, I'm not gonna, in this class, there's no math that you're gonna have on your test, but you have to have a general idea what speed is, okay? So in order to understand your speed, what we do is we take how far you relocated from position A to position B, and then divide it by the time over which it took you to get there. That's speed, right? So this says in 1 second you could go 10 meters, which is pretty, wow. I don't know, that seems pretty fast to me. So in 1 second, 1001, you go 10 of these. That's pretty fast, 10 meters per second, right? Yes, ma'am.
What was Kepler's second law again?
Kepler's second law was the one where I go fastest when I'm close to the sun and slow when I'm farthest from the sun.
What was his third law then?
And his third law, I know I used to get confused too. So the thing about his first law is it's just about one planet, or second law. The thing about his second law, it's just about one planet. You know, I'm going to move fastest there at perihelion and slowest at aphelion. The thing about his third law looks at all the planets. It says, takes a bird's eye view and it says, Mars goes slower than Earth. Earth goes faster than Mars. Jupiter goes slower than Mercury. Okay? So that's kind of the difference between those.
So it's like in order then. That's like, so the first one's just in one going around, and the second one is if they're in order, then this goes faster than this.
Yes.
Okay.
Yep. Good question. Because they do get a little confusing because I write down like, now how does that work? Does that make more sense then? Good. Okay, so speed, velocity, and honestly, sometimes we use those as the same. And you're like, speed, velocity, it's the same. And we use them interchangeably. What?
Velocity is direction.
Velocity is direction too, exactly. Exactly, that's the difference. So if I said that I'm going 60 miles per hour, okay, 60 miles in 1 hour, my car probably, right? That's speed, but if I'm coming to work from Burlington and I say I'm going 60 miles per hour due north, that's velocity because I've added the direction to it. Okay, so we have speed, velocity, kind of a little different thing. Okay, acceleration. What do you think when you think of acceleration?
Speeding up.
Speeding up, exactly. So like if I'm going 50 miles per hour now and then I'm going 60 miles per hour in a little bit, what I've done between those two is to accelerate, exactly. Accelerated 10 miles per hour, okay? Exactly. Acceleration is change in velocity. But now here's the deal. We said speed is speed, velocity is speed plus direction, and acceleration is change in velocity. So here we go. So speed is speed, velocity equals speed plus direction, and acceleration equals change in velocity. Now, here we go. We could change speed or we could change direction. Those are all accelerations. So here we go. This is what that looks like. We could call this scenario A, B, and C. These are all examples of acceleration. Acceleration is a change in velocity. Notice the first one, I sped up. The car was going 30 kilometers per hour. At the end of its gathering data, it was going 60, so it increased 30 kilometers per hour, right? This one down here, I'll go to C. This one is coming to a stop. It changed velocity. Why? Because it changed speed. It didn't change direction, but it changed speed. So this one was going at 60, so what we call deceleration is really acceleration in general. So when something slows down, did it change velocity? Yeah. This also is changing velocity. Now, it's not changing speed, 60 to 60.
Changing direction.
It's changing direction, exactly. So when something goes on a curve like that, what we could do at any given moment in time is to draw a line kind of like tangent to its motion. So here we go. This is how this car right here is going this way. 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 So if you compare how it started to how it finished, I'll put it at just an F here. It started going this direction and it ended going this direction. Okay, so when you're going around a curve, even if you keep the same speed, you're changing direction. So that's changing velocity, and so that means that you're accelerating.
Okay, just so I get this straight. Acceleration, that car, it was a change in velocity, even though it didn't change directions, it changed speed.
Which one? A, B, or C?
C, I mean.
C? Yes, it changed
So,
speed.
That's why it's still a change in velocity, because it, okay.
Yeah. This one slowing down is also acceleration,
So
even
it
though
doesn't have to change directions.
it doesn't have to change direction. No. So if we kind of apply that to the planets now, and we're going to actually get to that on Wednesday a little bit, if I draw up, there's the sun, and here's the planets, okay? Do you guys buy this? The fact that the planets, let's take out, if it's okay with you, let's take out Kepler's second law, and let's just assume that the planet goes at a constant, which it doesn't. Let's just say it goes at a constant speed. Since it's got that shape, okay, even if it was going at constant speed, does it seem like it's accelerating to you? Does this make sense? These are my planets, and it's just like this.
Yes.
So my planets are accelerating all the time because they're changing direction all the time, exactly. So we'll talk more about that on Wednesday. Are we on past Wednesday? Yes, you guys are lucky. You guys made the cut. So homework is due Wednesday. Don't forget to get that done, guys.
We can go.
What?
We said homework is due. We gotta do 3 of them still.
Yeah. For the previous part that we just did on the.
You said it doesn't tie down with religion, like with Jupiter and them. You said it doesn't tie down with. You said it's not equal to religion.
Right. Science is not equal to religion. Yeah.
I would think it would be because Jupiter is down to the sky too, right?
Jupiter's in the